Welcome to Finite Element Methods Abaqus tutorials. I'm Leonardo Araque, a PhD student at UCLA, and I will guide you through this tutorial. The purpose of this tutorial is to model a thin wall pressure vessel in 2D and 3D and compare the results with the hand calculations. From strength of materials, the maximum principal stress is the tangential stress sigma theta, which is the product of the internal pressure and the ratio of the inner radius and the wall thickness. To consider a cylinder as a thin wall, this ratio should be larger than 20. Another consideration is, for this analysis, is consider a long cylinder with a closed ends. It means that a plane strain analysis is suitable for this type of problem because the deformation and the state of stresses in a cross-section area is repeatable along the cylinder. So let's move and let's start with the modeling in Abaqus. The first, to rename the model 2D so we can have better track organization. Now we move to the module part to create a part. So the inner radius for this pressure vessel is going to be 120 millimeters and the wall thickness 5 millimeters. So in the model space, we select 2D planar deformable shell with 250 millimeter size for the grid. And then we proceed to create the cross-section. So the outer radius for the cross-section is 125 millimeters. And the inner radius for this cross-section is 120 millimeters. When the section is created, we can move to the next module to assign the material properties. So the material for this model is steel whose mechanical properties are defined by the Young's modules and the Poisson ratio. So the Young's modules for steel is 210 gigapascals, and the Poisson ratio is 0.3. Next step in this module property is to create a section. The section is a solid homogeneous and is associated with the material steel. Click in the section plane strain for the model. Last step is to associate the part with the section. Now we can move to create the instance in the module assembly. This is a dependent instance, and once the instance has been created, we will proceed to create the load step in the module step. To create a step, we should rename the step and make sure that it's a static general. We are not using incrementation to apply the load, so we just can close this window. Now we proceed to assign the magnitude and the location of the distributed pressure. So by clicking in creating load, we can rename first. We can first rename the step. Make sure that the step is load, and from the category mechanical, select pressure. Next step is to create the surface, which is the inner wall for the pressure vessel where the load is applied, and assign the magnitude for megapascals. Now we can proceed in the module mesh to mesh the part. Make sure first to switch to part to be in agreement with the instance we created, and then get back to see the part. I want a global size of 2.5 millimeters, so I can have 2 elements through the thickness for the final element analysis. To assign the element type, we select from the element library a plane strain, linear interpolation without reduced integration element. The result is a 4-node bilinear plane strain quadrilateral. Oh, I forgot to uncheck the reduced integration. All right, so last step is to mesh the part, and we can verify that we have 2 elements through the thickness. Now we can proceed to create a job, but before doing this task, I will continue with the creation of the 3D model. So the 3D model is a 3D space deformable solid. I'm going to use revolution to create this model. And the approximate size for the grid is in agreement with the length of the cylinder. So let's say that the length of the cylinder is 1 meter. And I'm not going to model the entire pressure vessel cylinder. I'm going to save time, computational time, by modeling only a quarter of the cylinder. In meantime, I will use symmetry in my model. So we start by creating the profile. The length for this horizontal line should be the same as the outer radius, which is 125 millimeters. The length of the outer wall is 0.5 millimeters. Sorry, 0.5 meters. So it's okay. Now let's move to create the thickness of the wall. Five millimeters. This internal wall has a length of 495 millimeters. So now we can continue with the profile. So this horizontal line will help us to close the cross section, and with this vertical line. So the profile has been created. The next step is to revolve this profile around some axis. Since we're doing a quarter of the cylinder, that would be only 90 degrees rotation. So this is the result. The next step is going to the module property to create a material, which is pretty much the same. We need to follow the same steps as we did earlier. So the Young's modules is 210 e to the 9, so 210 gigapascals. The Poisson ratios is 0.3. We create a section. This is a solid homogeneous section and is related with the material steel. This time, the part is associated with the creation, with the section created before. So now we can create an instance in the module assembly. It's also a dependent instance. In the module step, we can create the step to later apply the load. So remember to select a static general. We're not doing incrementation. So we can define now the apply the magnitude of the load. So the load, let's name it load, make sure that the step is load, and from mechanical, from the category mechanical, and the type pressure. Continue. So I'm gonna select this view to apply the load. So we need now to select the surfaces. So this is the inner surface, and for the cylinder, and this is the inner surface for the end cap. So hold shift and click in this surface as well. Those are the surfaces where the load is applied. So just click done and define the magnitude of the load, which is 4 megapascals. For this problem, we need to apply some boundary conditions because we're using symmetry. So let's create the first boundary condition. Make sure that the step is initial, and from the category from mechanical, select symmetry. So first, I'm gonna use this, apply the symmetry along the z-axis. So I need to select these areas, these surfaces. This surface, right? Once this is done, I select symmetry in the z-axis. Now I'm gonna switch to this new view to apply the symmetry in the x-axis. Make sure we have the same setting, step initial, category mechanical, and type symmetry. Select the cross section or the face. And make the selection of XM. We only left to apply the symmetry at the bottom of the cylinder, which is in the y direction. So we can do it from this view, I guess. Yes. So again, go to create a boundary condition, make sure that the setting is the same, select this surface, and click on symmetry in the y direction. All right, so we are pretty much done. We are done with the boundary conditions. Now we need to proceed to mesh. So to mesh the part, we're gonna use hexahedron elements. So for this purpose, we need to do some partition first. So go to create a partition. Let's create a cell, and let's create a partition by extending a face. I need to get back to part. Okay. So this is extended face. So this is the internal face, is the one we're going to extend, create a partition, and I think this is done. So you can see right here the partition, and we flip to the other side. you can see the partition as well, right? Okay, let's see if this is enough to proceed with the meshing. So next step is to see the edges. I'm gonna use this technique because I expect to have a stress concentration around the end cap, right? So I want a more dense mesh on that location to capture the mechanical behavior of the elements. So I'm going to select this, I'm going to select these edges. So 1, 2, and on the other side, notice here. Okay. Let me check something first. Oh, it seemed like the partition was not created properly. All right, give me 1 second, because that's important for the purpose of the analysis. Okay, let's see what happened. So, oops, I can select the edges. All right, done. So I'm gonna switch to by number. My bias are gonna be just single bias. I want 30 elements along the edges. I'm going to increase the bias ratio to 10, and we're going to apply that. So you can see that with this procedure, I will guarantee a more dense mesh around the end cap. Okay, I'm fine with that. So we're gonna do pretty much the same for the end cap edges. So this view will help me with this. Yep. So I'm gonna select these edges. These two. All right, this is done. I'm gonna use the same bias. All right. From here, from these two edges, I'm gonna use non-bias, just 30 elements for all of them. What's wrong with this? Okay. So, all right, what about this? That the opposite end of the cylinder, we also need to apply some, we need to see that edge as well. So I'm gonna select this edge. And let's do 30 elements as well. All right, so I think we're pretty much done. Once this is done, we go to assign mesh control. We select the entire part. We select hexahedron and click OK. We're done. Let's proceed with the mesh. And now let's see what's the result. So the result is we have a denser mesh at the end cap, right? And less dense mesh at the opposite end. All right. Okay, that's good. So it looks good. So now the next step is to create a job for both models, 2D and 3D, to complete the analysis. So since I'm doing it simultaneously, I go to viewport. I'm going to create an additional viewport, and to see the two models, I select in the same viewport tile vertically. My left-hand side is going to be for the 2D model, and my right-hand side viewport for the 3D model. So let's start by creating the job in the module job for the 2D model. I name this job as 2D. I'll do the same for the 3D model. All right. Let me see if I'm doing it right. Yes, that's right. So let's submit the jobs. And we can follow the progress in the message window at the bottom of the screen. All right, both has been completed successfully, so we can move to see the results. All right, let me see. All right, so we have the results in the 2D ports. Let's check first the maximum principal stress in the 2D model. So I would probe this part. Let's do it here. Let's check this. All right, so we're probing nodes, and the values for the maximum stress in the inner wall are 97.5 megapascals. in the middle, in a node, in the middle section is 96. And finally, in the outer surface, with a node in the outer surface, we have 94.5 megapascals. All right. So that's the results for the maximum principal stress in the 2D model. Let's repeat this and this. Let's compare the results with the 3D model. All right, so let's put the value for the 3D. So for the node in the inner wall, we have 97 megapascals. For a node in the cross section, the middle cross section, we have 96 megapascals. And in the outer section, a node in the outer surface, sorry, we have 94.33 megapascals. Let's see really quick how it distresses at the end cap. So we can see that the highest stress is at the union between the cap and the body of the cylinder. So, and I think that was expected, right? Because you have a perfect spot for a stress concentration. All right, so with this, I finished this tutorial. Please compare the results with the hand calculation and make your conclusions. Thank you so much.